Now let's look at an example. Okay. So suppose we have a signal xn, a discrete time sequence xn, that has Fourier transform that is 0 from 2 pi over 9 up to pi. Okay, so basically it's saying that the bandwidth of the signal is 2 pi over 9. It could be non-zero below 2 pi over 9. Okay, so your signal may look something like this. So this is x e to the j omega. This is pi, 2 pi, minus pi, minus 2 pi. Okay? So roughly, suppose this is 2 pi over 9 minus 2 pi over 9. You have one replica here and one replica here. Okay. So suppose you're asked to find n such that omega s, which is 2 pi over n, is greater than 2 times 2 pi over 9. Okay. So suppose that you want to sample this signal in a way that allows you to reconstruct it afterwards. Then you need to sample at a rate that is greater than 2 times the bandwidth. Okay? So this means that the period of your sampling cannot be too large. Right? If capital N is too large, meaning that you're sampling too far away, right? You're not getting enough samples to reconstruct the signal. Okay? So what is there should be a maximum value of n that will allow you to still reconstruct, right? That will allow you to satisfy the Nyquist sampling criterion. And by this, right, just by moving n to the other side, you find that this n is bounded by 9 over 2. Okay? But n must be an integer, so hence the maximum n is 4, and the sampling frequency is omega s equal to 2 pi over 4, which is pi over 2. Okay. Okay. So if you pick n, to be, small enough such that you're sampling at a rate greater than 2 times the bandwidth, then you have replicas of the spectrum that do not overlap with each other, and therefore you can reconstruct by passing it through an ideal low-pass filter. Okay. So this operation is described in this page here. Okay, so without aliasing, your signal can be reconstructed by passing this impulse train sampling signal through an ideal low-pass filter. And in the time domain, this is taking the convolution of this impulse sampling signal with the impulse response of an ideal low-pass filter, which is something that is, corresponding to a discrete time sinc function. Okay. All right. So if you look at the this figure here, you can see that you start out with x, right? This discrete time frequency, the frequency the Fourier transform of the discrete time sequence, right? When you sample, right, this is repeated at every integer multiple of omega s, okay? Then as long as there's clear separation between adjacent spectrums, you can pass this through a ideal low-pass filter. This should be H, okay? This should be H. Through an ideal low-pass filter, okay, to get back this spectrum here that is the same as the input, okay? All right. So this operation gives you an exact interpolation of the original signal. Right. So if you plug in this sinc function inside Hn here, you get the summation x kn n omega c over pi sine omega c n minus kn over omega c n minus k capital N. Okay, so this is the exact interpolation similar to that in the continuous time case. Okay. All right, so when we talked about sampling on continuous time signals, we said that the motivation is to convert continuous time signals to discrete time so that we can perform discrete time processing, okay? But if we start out with a discrete time signal, why do we want to perform sampling anyway, right? So the thing is that, sometimes you may sample too much, right? If you sample too much, when you perform the processing, the complexity clearly depends on how much samples you have, okay? So if you're sort of oversampling your signal, then this may increase the complexity of your processing, right? So to reduce the complexity of your processing, right, this motivates us to further sample this discrete time signal to get less samples. All right. Okay, so suppose that this is your original discrete time signal where you are oversampling, okay? So oversampling, so if you look at it from a frequency domain perspective, oversampling gives you a spectrum that looks like this with a very large separation between adjacent spectrum, okay? So if you look at this, it seems that we're not having a very efficient use of the spectrum, okay? So in fact, if you further sample this signal, you get these replicas that are closer and closer to each other, meaning that we're fully utilizing the spectrum, okay? And as long as they do not overlap with each other, I can still reconstruct the original information. So this means that using less samples still allows us to preserve the original information. So it's not necessary to use so many samples at the beginning, okay? So originally we have so many samples, but if we can, just take a subset of these samples, but still are able to reconstruct the original signal without distortion, then we would prefer to use less samples, right? Because this imposes less complexity on our processing, okay? So after sampling, right, you see that there are a bunch of zeros in between. So, memory-wise, you still need so many memory to record all these values, which is not efficient, okay? So what people do is that, we just construct another sequence that just basically removes these zeros, okay? So let's call this XBN, right? So to avoid redundant representation of all these zeros in between, we just define XBN as these non-zero sampled values, XP at integer multiples of capital N, or basically the original X at integer multiples of capital N, okay? So you can call this decimation, or you can call this downsampling, right? So we are taking something that is oversampled, right, sampled more than necessary, and we're downsampling it to something that is more compact, okay, more concise, okay? Right, so this is called decimation or downsampling. Okay. Now, it's interesting to see what is the relationship between the downsampled signal, the spectrum of the downsampled signal, with the spectrum of the original sampled signal, or the spectrum of this XP, before removing the zeros. Okay. So intuitively, what would be the relation between the spectrum of this and the spectrum of this? Okay. Intuitively, you could probably already imagine, because if you compare these two, right? Yes, you're compressing the time domain signal, right? You're compressing the time domain signal, right? So in the frequency domain, the spectrum of this should be stretched compared to the spectrum of this, right? And we can see that mathematically, right? So suppose we derive the Fourier transform. Right, so this can be written as summation k of x p k n e to the minus j omega k, okay? Because xbk is just xpk times capital N. All right? Now, I can perform a change of variable where I set n equal to k capital N, so that now I have a summation over xp n e to the minus j omega n over capital N. But the thing is, now this should be non-zero only when n is an integer multiple of capital N. So we're not summing over all n, but summing over n that is equal to an integer multiple of capital N. Okay? But making this restriction really is not that necessary, because if you look at xpn, xpn is only non-zero over integer multiples of capital N anyway, right? For all other values, it is 0. So it's okay to sum over all n, because for all values that are not equal to integer multiple of capital N, xp is 0 anyway. So I can write this as summation n from minus infinity to infinity, xpn e to the minus j omega n over capital N. Okay? And this is exactly the spectrum of xp of e to the j omega over capital N. Okay? So if you compare xp with xb, you're compressing the signal in time. So in the frequency domain, you're stretching it out by capital N. Okay? So let's take a look at what it looks like. Okay. So this is the spectrum of the original signal x. Right? It's discrete time, so the spectrum is periodic with period 2 pi. Now you sample it, right? You sample it at integer multiples of capital N, so you will get several replicas of it at integer multiples of the sampling frequency. So in this example here, you can see that there are 3, so capital N is probably just 3. Okay? So you can see here that you get N equal to 3 replicas for every 2 pi, right? Because every one of this is repeated at integer multiples of omega s. That is 2 pi over capital N. Okay? Now,